Hello, everyone, and welcome to Fermilab's Art and Lecture Series at Home. My name is Lex Sexton Kennedy. I'm the CIO of Fermilab, and I'll be your host for this evening's lecture. I would like to introduce tonight's speaker, Jennifer Rapp. Jen is a senior scientist and head of the Dune department in the neutrino division at Fermilab. Her research focuses on neutrino physics and searches for rare decays that are enabled by the very large size detectors and low background environments that are required for neutrino experiments. She specializes in detector instrumentation with a particular interest in liquid and gaseous argon time projection chambers. And with that, take it away, Jen.
Okay. Thank you for that intro, and thank you all for giving me the opportunity today to tell you about a few of the useful applications of particle physics that have been made possible by fundamental scientific research at Fermilab. Before I start, I want to thank Valerie Higgins, Tom Kroc, and Eric Ramberg, all of whom helped me gather images and information regarding past medical applications at the lab. The title of my talk came from a question my mom asked me a long time ago when I was in grad school, which at the time I struggled to answer. She said, "So how does your research affect my everyday life?" And to be honest, I was a little annoyed with the question and a little embarrassed that I didn't have a good answer. And I think what I said was something like, "Well, we're not setting out to invent new practical tools, Mom. We're just trying to understand the mysteries of the universe. But sometimes in trying to understand the mysteries of the universe, we develop something that ends up having a practical application in everyday life." And I thought that was an okay answer, but it wasn't good enough. And so she asked again, she said, "Like what?" And again, I couldn't give a great answer. So I hope I can fix that today and tell you about just a few of the things that have ended up being useful applications that arose from our fundamental scientific research at the lab. Many of the tools that we use today in medicine for diagnosing problems or providing therapy incorporate technology that was originally developed by physicists in our quest to explore the fundamental nature of matter or the mysteries of the universe. From the past, this includes the development of superconducting magnet technology, which is what enabled magnetic resonance imaging or MRI. And that's what's shown in the two right-hand bottom images. And also the idea of using particle beams for treatment of cancers, which is shown in the top two images. I don't have time to cover everything from the past, so today I'm choosing to tell you a bit about radiation therapy, and the rest of the talk will focus on the present, where I and about 10 of my Fermilab colleagues volunteered our time to work with a group of scientists and engineers across the world on a project to design this respiratory ventilator that's shown in the bottom left image. And this was, of course, in direct response to the ongoing COVID-19 pandemic. Let me start with the past. So in particle beam or radiation therapy, physicians will treat cancer by directing beams of particles at cancerous cells. Those beams are intended to damage the DNA strands of the cells, destroying their ability to divide and grow. But at the same time, you don't want to damage nearby healthy tissue. This idea of using radiation to treat cancer has been around for more than 100 years, as you can see in the timeline here. Even before 1900, scientists were using X-rays from radioactive sources as a form of clinical therapy. And you can see how much that's developed over the years, such that now there are dedicated facilities for beam therapy with protons and other types of particles. But let me highlight this box in 1946. This was the first idea to use protons to treat cancers, and this is directly related to some work that was done at Fermilab. That idea came from Robert Wilson, whom many of you will already know was the first director of Fermilab, although he had this idea a long time before Fermilab existed. Wilson's interest in the medical use of high energy particles grew from some neutron therapy work that he had witnessed when he was an undergraduate and a graduate student at the University of California, Berkeley in the 1930s. In the 1940s, then, he wrote a paper, and a clip of that is shown in the upper right. It was called Radiological Use of Fast Protons. And it was published in this journal called Radiology, which is not a journal that particle physicists typically publish in. The important takeaway from that paper is this sentence that I've put in the center here. It says, the dose is many times less where the proton enters the tissue at high energy than it is in the last centimeter of the path where the ion, he means proton, is brought to rest. So let's unpack that and see what he means there. Here we can look at the difference between the original type of cancer therapy using X-rays and the new proton therapy that Wilson proposed. So as particle physicists, part of what we do is observe and understand how different types of particles will interact with matter. And that's usually inside our detectors. But the protons and other charged particles have a very particular way of depositing energy, and that's what's shown in this graph. So the vertical axis is showing you the radiation dose, which you can think of as the amount of damage the beam is doing to the material that it's traveling through. And then the horizontal axis shows you how far the beam has penetrated into the material. So you can see that the gray curve, which is X-rays, has a lot of damage that happens near the surface of the material within a few centimeters. And as it travels deeper and deeper into the material, it does less and less damage. The orange curve shows this special feature of heavy charged particles like protons. When they enter, they're doing only a small amount of damage. And as they get deeper into the material, they start to do more and more damage. And then they do the most damage at the peak there. And then the damage drops suddenly almost to zero. That feature, the peak, which is known as the Bragg peak, is a well-understood physics behavior of charged particles coming to a stop in materials. And the distance or depth that it occurs in the material is directly related to the energy of the proton. So you can basically decide at what depth you want that peak to occur by adjusting the energy of the protons you're using. That peak is something that we as particle physicists exploit in our experiments to understand what particles we're looking at and what energy they had. But what Wilson realized, which was the key point, was that this very distinct pattern of energy deposition would allow you to precisely target a tumor without damaging nearby critical organs. So the protons would do a small amount of damage on the way to the tumor, maximum damage at the tumor, and then no damage after the tumor. That's in contrast to what you see with the X-ray therapy, where the beam continues to do damage after the tumor as well. Now, protons and X-rays are not the only types of particles you can use for therapies. Other options include gamma rays, electrons, neutrons, and heavy ions. So how do you choose what's the best therapy? Well, there's no simple answer to that, but there are a number of important factors to consider. So this graph tells part of the story. You'll recognize the shape or profile of the energy deposition for protons, the one with the Bragg peak, and X-rays that we were just looking at in the previous image. But now you can see the other types of particles shown. So you might imagine that for skin cancers or other cancers within a few centimeters of the skin, gammas or electrons might be pretty effective, but you probably wouldn't choose protons for that case. But this shape that you're looking at, the shape of how the radiation dose is distributed, is not the whole story. It's also important to consider how much damage per unit length is being done by the particles. And that is known as linear energy transfer, which is abbreviated as LET. For photon or X-ray, electron, and proton radiation, which is known as low LET, the damage is done primarily by the beam interacting with electrons in the cloud of electrons that orbit the nucleus of an atom. So that's what's shown in this image here. When an electron gets pulled out of the atom's cloud, that's called ionization. For high LET particles like neutrons and ions, in the end, the damage is done in this same way by creating ionization, but it creates more ionization because the incoming neutron or heavy ion first interacts with the protons or neutrons in the nucleus, and some of those get knocked out and travel past other atoms pulling electrons out of their respective clouds. So instead of one particle knocking an electron out of the cloud, like low LET radiation does, the neutron shakes things up more and causes many secondary particles to knock electrons out of the clouds of other atoms. And you can see the difference in the cartoon on the right, where the density of dots represents the amount of energy that's left along the path of the particle. And that's correlated with the amount of damage it's doing to the cell. If a tumor cell is damaged by low LET radiation, it has a decent chance of repairing itself and continuing to grow, which is not what you want. With high LET radiation, the chance for a damaged tumor cell to repair itself is much smaller. So that's something else to consider when you're deciding which kind of therapy. That's still not the whole picture though, because different types of radiation therapy also have different levels of biological effectiveness, depending on the location or type of cancer tissue. And that level of effectiveness is quantified by comparing how much dose of a certain type of beam therapy would be needed in comparison with conventional X-ray therapy. So that's what's shown in this plot. So in the plot, you're looking at the vertical axis shows you the cell survival rate. So 1 means 100% of the cells have survived. And that's shown as a function of the radiation dose, which is in units of grays. So it's good. You see when you have 0 radiation dose, 100% of the cells survive. So that makes sense. And then if you look at, let's say you wanted to kill 99.9% of the cancer cells, that corresponds to 0.001 on the vertical axis. And if you were using neutrons, you would need 7 grays of neutrons, that's the red line, to kill 99.9% of the cancer cells. By contrast, in the blue line, which is showing you X-ray therapy, you would need 28 grays. So that's saying that neutron therapy has a relative biological effectiveness, or RBE factor, that's 4 times greater than that of X-rays. And then of course, cost is a factor. The least expensive therapy is usually from X-rays. Neutrons are not that much more, and then things start getting more expensive when you turn to protons and other heavy charged particles. I should also pause here and say that I'm not a medical doctor, so I'm sure there are other factors that need to be considered for each individual patient. And so please don't take this as medical advice. It's just to give you a sense of what types of information the oncologists will consider when they're deciding your treatment plan. And hopefully you never actually have to put this knowledge to use. So now that you understand some of the differences among the different types of radiation treatment and some of the biological factors to consider, let me show you how Fermilab was involved with radiation therapy in the past. So there are 2 independent radiation therapy facilities that Fermilab was deeply involved with. The first was the design and operation of the Fermilab Neutron Therapy Facility, the picture which is shown on the left. And the second was the design and construction of the first hospital-based proton accelerator for cancer therapy in the US. Fast neutron therapy began in the US in the early 1970s through a series of grants from the National Cancer Institute. At Fermilab, the interest in doing this grew from a presentation at a particle accelerator conference, which then led to some discussion among Chicago area physicians and physicists. And then it really got started with one of those National Cancer Institute grants. And that enabled the lab, partnered with the National Cancer Institute, to set up the neutron therapy facility. And patient treatment started there in 1976. So let's look at where it was. Here's an aerial view of Fermilab, which you may have seen if you've flown over in an airplane before. The big rings are parts of the accelerator complex, but the neutron therapy facility comes at the very beginning of that chain. So let's zoom in. If this talk had been in person, we would have been together in Ramsey Auditorium, which I'm pointing out there. And right next to us would have been the start of the Fermilab accelerator chain, which is a linear accelerator, which is often, you'll hear people refer to it as a LINAC. That's what does the initial acceleration of protons before they get injected into the other parts of the chain, including those big accelerator rings. So the neutron therapy facility was located partway down the length of this LINAC. Since the accelerator complex operates on a time cycle, and the LINAC is only accelerating particles to deliver to the rest of the chain for a fraction of each cycle, its free time can be used to direct particles elsewhere. So we have this option to bend protons out of the linear accelerator into a branch like the one that's shown in this diagram. The branch for the neutron therapy facility was located about a third of the way down the full length of the LINAC. So the protons were not yet accelerated to the full energy that they have by the end of the LINAC, but instead they were taken off at a lower energy that was chosen to be what they wanted for the neutron therapy. We can't bend or focus neutral particle beams like we can charged particle beams. And so the best you can do is focus the proton beam before it hits the target. And then most of the neutrons that are created when the proton hits that target will go in the same direction as the protons. So that's what was done. The protons were focused onto a metal target that's located at D in the diagram. And then a bunch of neutrons were created when the proton smashed into that metal. It was a chunk of beryllium. And then if you want to select some part of the neutron beam, for example, in a specific angular range, you can do that using something called a collimator. And that's what's happening at E. The patient sits in a room on the right next to basically a hole in the wall at the exit of this collimator, and the neutron beam exits that hole. So here's an actual collimator. Each one of them, that's the man's holding it and he's about to insert it into that hole. Each one was custom made for the patients from concrete and plastic. And if you look closely at this one, you can see that the cutout in the center has a strange shape to it. It was made to match the shape that they wanted to irradiate on the patient. The guy who's holding this collimator was one of the radiation therapists who operated the neutron therapy facility. Here's the treatment room, and you can see that the patients got very carefully positioned. The laser beam crosshairs that you see are an alignment system to make sure that the neutron beam would hit the correct location on the patient. Obviously, you don't want the patient to move during the treatment and accidentally irradiate other parts of themselves. And so that's why you see them strapped in. But the platform that they sat or stood on could rotate and translate, so the radiation therapists could move them if that was required for their treatment plan. This facility also has a nice, more personal side to the story as well. The man you see here is named Don Young, and he was one of the very first employees at Fermilab and was involved with the planning and building of the neutron therapy facility. You can also see him in the upper right in that lab newsletter that was printed in 1975, a week before I was born. In the year 2000, after Don had retired from the lab, he was unfortunately diagnosed with an advanced case of prostate cancer, and he chose to have neutron therapy at Fermilab rather than surgery. The cancer treatment was successful, and the neutron therapy left him cancer-free, and he lived to be 90 and died of natural causes just a few years ago in 2012. So this neutron therapy facility has done good. It's sadly no longer operating, but it ran for 36 years from 1976 to 2013, and it treated more than 3,000 patients during that time. The second aspect of particle beam therapy that Fermilab was involved with is the complete design and construction of a compact proton accelerator that's specifically for proton therapy, which is shown here. As you can see in the image, it's really small. It's only 20 feet across. And for scale, you can see that man sitting in the middle of the blue ring of magnets. He's not a patient, by the way. He's one of the people who built the accelerator. The inset on the bottom left is showing you what the inside of the magnets look like. These were all designed and built at Fermilab, and the full system, including computer-controlled beam delivery system, was also from Fermilab. It delivers protons in a range of energies to a set of treatment rooms that are not shown in this image. So the story of how and why Fermilab was involved is this. The guy you see on the second from the right is Dr. James Slater, and he was the director of a place that was then called the Loma Linda University Medical Center. He and a few of his buddies made the decision that they wanted to build a dedicated proton therapy facility at their hospital. And so he called Fermilab. The person he spoke to was Philip Livedall, who at the time was a deputy director of the lab, and he's the one in the white sports jacket on the left. And you'll also recognize Robert Wilson as the third from the left in that photo. So anyway, Slater called Fermilab and said, "Hey, what would it take for you guys to build an accelerator for us?" And they had this conversation, and Wilson and Livedall went away and decided that this was a good plan. And in 1986, Fermilab and Loma Linda University signed an agreement that Fermilab would build this accelerator facility. The project moved pretty quickly. It only took 2 years for the lab to design and build and assemble and test all of the magnets. And then they took it apart, packed it up, shipped it to Loma Linda in California, and shipped Philip Livedall along with it so that he could lead the reassembly and commissioning. And the center treated its first patient in October of 1990. So it was just 4 years from concept to actually functionally treating patients. Much like the neutron therapy case, there's a personal example of someone working on the project directly benefiting from it. So Livedall himself became a proton therapy patient in 1991. He was the first Loma Linda prostate cancer patient that was treated only by proton therapy without receiving any other treatments. And again, it worked. The cancer never came back, and he lived to be 88. So unlike the neutron therapy facility, the proton accelerator at Loma Linda is still operating. The Loma Linda Cancer Treatment Center celebrated its 30-year anniversary almost exactly 1 month ago on September 17th, and it has treated more than 21,500 patients with proton therapy over the last 30 years, and it has no plans to stop. Due to the success of that facility, there are now about 40 operational centers in the US and 70 more around the world. And another 40 are under construction in the US and internationally, including in South America, Africa, and Australia. So this idea that originally came out of an understanding of particle physics has made a big impact throughout the world for the still relevant problem, cancer. For the rest of the talk, let me transition to the more recently emerging ongoing global problem of COVID-19. So obviously, everyone knows that this pandemic is doing terrible things across the world. This graph comes from a nice interactive tool that the Financial Times has put together. It's showing the average number of new COVID-19 cases per million people, shown as a rolling 7-day average. I got this chart this morning, so it's the current snapshot of where we are relative to other countries. And as you can see, in many countries, new cases are starting to rise again, and it looks like they are here as well. To look at it more numerically, almost 40 million people have been infected across the globe, and there have been more than 1 million deaths caused by this virus. In the gray graph under active cases, you can see that the number of new cases each day is still in the hundreds of thousands across the globe, and it's increasing. And deaths per day are in the thousands. That's just to highlight where we are right now. But let me start back in March when it was acknowledged that this had become a global pandemic, and Italy was really starting to see the effects. So when Italy was just starting to see a very steep slope in that first graph that I showed you, meaning that every day had even more new cases than the previous day, an Italian colleague by the name of Cristiano Galbiati decided that he wanted to do something about it. He's a professor of physics at Princeton, but he was in Italy working on one of his experiments, and he got stuck there because of the virus. His father and brothers, all of whom live and work in Italy, are all real doctors, by which I mean medical doctors. And so he was hearing first-hand reports about how bad things were in the hospitals. One of the hardest hit regions of Italy was Lombardy. And in that region, 9% of the patients that were hospitalized for COVID-19 required intensive care. And of those 9%, An enormous fraction of them, 88%, needed invasive mechanical ventilation, meaning they needed to be intubated. So within about a week of Cristiano's initial idea to gather people to do something, he had already gotten plenty of particle physicist volunteers from his experiment in Italy. And I became aware of the plan through a Fermilab colleague who works directly with Cristiano on that experiment in Italy. I was feeling stuck at home at the time and helpless to do very much. So it seemed like an attractive prospect to participate in this. But what does that actually mean? So at the time, there was a shortage of ventilators in Italy, and there were projected to be shortages in the US and Canada as well. So what could we, a bunch of particle physicists, do? Well, if you think about it, a ventilator at its very simplest just needs to deliver a regulated volume or pressure of air and oxygen at its output, which is where the patient is connected. And this is not that different from some of the systems that we have to design for our particle physics experiments. We sometimes need to deliver and regulate precise volumes of pressurized gases for our detectors. The critical difference is what's at the other end, a human or an inanimate object that's collecting data to understand the mysteries of the universe. So the stakes are much higher in the case of the ventilator. So we decided we would do this, and here it is. It's called the Mechanical Ventilator Milano, or MVM. Now, let me tell you how we got to this end product. But before we get into the design, let's go over the basics of normal ventilation. So for any of you with a medical background, I apologize in advance for my simplified physicist's description of how ventilation works. The base principles are physics, but I won't get into any of the more complicated biological and physiological aspects because I can't. So to start, just think of your chest as a closed box. There's only one path for the air to go in and out of the lungs, and it can be closed off if you hold your breath. When we're breathing, the diaphragm is moving to either increase the available volume for your lungs to fill or to decrease that volume. Now, the laws of physics tell us that if you have a closed system like your chest, or like these containers in the top center image, then when the volume increases, the pressure will decrease, or when you decrease the volume and keep the amount of gas or liquid in there the same, then the pressure of that gas or liquid will increase. Our respiratory system is not completely closed though, because we can add or release air from the lungs through our noses and mouths. So another principle of physics says that if you connect two systems with different pressures, the material, which is gas in this case, will flow from the higher pressure side to the lower pressure side. So when your diaphragm expands the volume, it causes the pressure inside your lungs to be lower than the pressure of the room, and your body inhales to equalize the two pressures. When you've filled your lungs, then the diaphragm pushes up to contract the volume, causing the pressure inside your lungs to increase, and then it becomes greater than the ambient pressure of the room, and your body exhales to equalize the pressure again. So that's how it works if you're breathing naturally on your own. But what if your body isn't doing the breathing correctly? That's when a mechanical ventilator becomes necessary to create a pressure difference and make air move into and out of your lungs. So let me tell you about two of the ways that you can create pressure difference to get the air in and out of your lungs. When mechanical ventilators were first invented, the most common type was called negative pressure ventilation, which is what you see on the left. So in this case, the patient's body, whole body, or sometimes just the chest, although hopefully not cutting him in half to do that, is inside some closed box. And the head is outside the box. So if you pump the air out of the box, then the pressure inside the box is decreased relative to the ambient room pressure. And then the air will flow into the lungs to equalize that. To get him to breathe out, you pump the air back into the box. So now it's at the same pressure as the room. And then that makes the lungs be at higher pressure and the air will flow back out. So this just artificially creates exactly the situation that your diaphragm and lungs do when they're operating correctly. It's completely non-invasive and the patient can talk and eat. And so when mechanical ventilation was first being used, this was pretty popular, although it's less often used now. On the right side is another way to create a pressure differential by so-called positive pressure ventilation. So in this case, you cover the patient's mouth and nose or insert an endotracheal tube so that you can use a device to apply pressure that's higher than the ambient room, the atmospheric pressure. So you're pushing air into the lungs, and then to get the patient to breathe out, you just remove that applied pressure, and the now higher than ambient room pressure that's inside the lungs will flow back out. So in writing this talk, I did a little bit of research, and I found the first description of a negative pressure ventilator was this full body type that's shown on the left called a tank ventilator. It was invented much earlier than I was expecting. It was in 1838, and it consisted of an airtight box with the patient sitting up. It looks super uncomfortable. And then the pressure was changed by using that hand pump that you see sticking up from the box. On the bottom is a different design of the same type of device, and it's manually operated by pushing on the bellows that you see on top of the tank. So those early devices were further developed over the years, and they turned into devices like what you see in the photograph on the right. So many of you will recognize those as iron lungs, and they were very widely used during the polio epidemics from the 1930s to 1960s. So I mentioned that before that these days we more commonly use positive pressure ventilation. The idea of positive pressure ventilation came about partly from a need to assist the breathing of World War II pilots who were trying to fly at higher altitudes. So a man by the name of Forrest Bird, an amazing name, decided that he was going to do something about this, and he adapted some pressure gas masks that were used for working in mines to turn them into oxygen supplying face masks that ended up being successful and allowed the pilots to fly up to 35,000 feet, which was higher than they had gone before without passing out. So that experience made him interested in devices that could assist people with respiratory failure. And he invented a machine to help his neighbor who had emphysema, and I'll let him tell you about it.
It all began with a gizmo he cobbled together long ago to help a friend with emphysema breathe.
I went to the hardware store and got a doorknob. You can see this doorknob right here at the top. So the patient could take and push down like this on the doorknob and blow their lungs up. Well, he did remarkably well with it.
What year are we talking about?
We're talking about 1947.
Did you have any idea then that you were on the trail to a device that would be just the most routine part of emergency medicine there is?
No, sir, not the foggiest. I mean, this was seeing a problem and coming up with a rudimentary answer, that was all.
So that guy's amazing. That original breathing machine with the doorknob was what he later refined and which became one of the most widely used original positive pressure ventilators in the US and elsewhere in the world. It was known as the Bird ventilator, because remember his name is Forrest Bird, and that's what's shown on the left here. It was pressure driven, so it didn't require any motor or turbine or anything. And on the right, at the same time, in London, a man named Roger Manley had the same kind of idea, and he developed a similar ventilator that was also entirely gas driven. And that one became the most popular model used in Europe. Both of these were fully mechanical machines. They just required a source of pressurized air or oxygen to operate. The ventilator that we've designed during this pandemic is modeled after these two original machines. It has no motors or pumps. It just needs a source of pressurized air and oxygen, but it's electromechanical instead of fully mechanical. So it also needs an electrical outlet. The modern day upgrade of our machine is that the opening and closing of valves is initiated by a microcomputer. The we I'm talking about is the team of people who volunteered their time to develop the mechanical ventilator Milano. And it's a broad team of more than 100 people with synergies between research institutions, which are the universities and laboratories, medical experts, and private sector companies. We wanted this device to be as accessible as possible, and so we started with 4 simple design principles. The first was that it should be low cost. Commercially available ventilators can cost as much as $50,000, and they're typically in the $35,000 range. There's a reason those machines are so expensive. They have a lot of bells and whistles that we didn't intend to implement in our more simple machine. And in our machine, we were also able to use almost all off-the-shelf commercially available parts, which also keeps the cost lower. In the end, our machine is expected to be in the $5,000 to $6,000 range, so a factor of 7 to 10 cheaper than the commercially available devices. We also obviously needed the machine to be robust and reliable. From a hardware standpoint, that means that the fewer individual parts you use when building something, the less chance you have that a part will break. So it implies that you should use as few parts as possible. We also wanted to design something that was easy to manufacture in large quantities in a short amount of time for obvious reasons. And then finally, we wanted the overall design concept to remain open access so that others could design similar devices without having to fully reinvent the wheel. Here's the design. The components that make up the MVM are inside the light blue box that you see. And as I said before, it just needs an electrical outlet and a source of pressurized medical air and oxygen. That's available in most emergency rooms and intensive care units. But in the absence of a wall hookup for pressurized air, you can use a portable tank. So starting at the top left of the image, you can see where the air and oxygen enter a gray box that's labeled GB1. That is an off-the-shelf gas blender to allow you to adjust the fraction of oxygen that the patient breathes. So normal air that you breathe is only 21% oxygen, but sometimes it's useful to have patients with respiratory problems breathe air that has a higher percentage of oxygen. So after mixing the air and oxygen, it goes into the ventilator, and the ventilator is attached to the patient at the very bottom of this image. So you can imagine a patient mouth there just below the thing labeled F1. So inside the ventilator, the dashed lines that you see, those are all electrical connections, and the solid lines are all gas connections. So if you follow the black path, that's the breathing path, and it has, you'll see some side branches, those are safety features. And you'll also notice there are just a few valves and pressure regulators in the design. Those are all labeled with PR or V and a number. And that was in keeping with our design principle of minimizing the number of parts. The red solid lines you see are gas lines that are connected to sensors. So those are for reading the pressure or gas flow at various points in the system, including at the patient mouth. And the green lines there are gas lines that control pneumatic valves. The brains of the device are the pinkish box that you see. So that's the microcomputer that's supervising operations and deciding when to open and close the various valves based on what it reads from the sensors. So the project really began in mid-March, as I said, and by the last week of that month, we already had a rough prototype built. So here's that first prototype. That's a fake lung that you're looking at. Here's part of the breathing path. And those columns of water are just a way of regulating the pressure. That was definitely not intended to be in the final design, but it was a proof of concept that you could make the microcomputer control board do the correct sequencing of inhalation and exhalation on the specified time scale. So here's our second prototype, which was only a week later. So you can see in this one that we had eliminated the temporary water column method of setting pressures and moved to electromechanical regulation. So the corrugated clear tubing and the blue and green parts are just standard patient breathing circuit tubing that's used with ventilators. There's a large supply of those breathing circuits in hospitals, and the initial idea was to use that, but in the end, we found an even better solution. So here's the final prototype. So you can see a touch screen. It's much smaller, it looks more professional. And this white box is a virtual patient. We'll come back to that in a few slides. So you can see that the final device is more compact than the first two prototypes, which are shown in this last screenshot here. The original one with the water columns is at the far end of the table, and then the one with the corrugated tubing providing the air pathway is right next to it. So let me show you the inside of the final device. Here it is. As you can see, it's a much more compact and efficient use of space. That corrugated medical tubing has been replaced with a more robust design with a metal manifold, which is along the top there. And you can see there are electromechanical valves and pressure regulators mounted along the top on that metal block. We call that the fluidics block. This electronics board that you're seeing at the bottom of the image is what has all the pressure sensors mounted on it. And that's what the clear blue tubing is attached to. It also has things like an alarm loudspeaker and the connections for powering LEDs for alarms. And it powers the brains of the device, which are made up of a Raspberry Pi microcomputer and an Arduino. Some of you are probably familiar with those. They're little microcomputers that you can buy on Amazon or at your local computer store. And people like to use them to do DIY projects like turning on and off your lights or making an automated plant watering system or things like that. Anyway, these little machines manage the opening and closing of the valves and supervise the alarms, and they talk and listen to the touchscreen panel. The touchscreen is not shown here because, and neither is the Raspberry Pi and Arduino, because they're attached onto the back of the touchscreen that I had to remove to take this photo. The board that is shown is a custom board that hosts the various sensors, and those sensor signals are fed into the Raspberry Pi to allow it to decide when to open and close the valves. And then the Raspberry Pi sends back electrical signals that are sent off to the valves to put them in whichever state is called for at that moment. So this custom board is one of the few parts that wasn't off the shelf, but it's cheap and easy to make. The Raspberry Pi and the Arduino were programmed by a very talented group of physicists who are experts in writing data acquisition and triggering software for our particle physics experiments. So this was just another instance of needing to write software that would look at sensor data and make decisions on what state each of the machine's components should be in, and then also record that data and send it to the display for the doctors to see. So here's what the display panel looks like when you're standing in front of the machine. In this case, it's operating in one of its modes, and I'll tell you more about the modes in a minute. This is just a 7-inch touchscreen graphical user interface, and you can set all the operating parameters like how many breaths per minute you want, and what's the maximum pressure that should be provided for the inhalation. And the waveforms are showing you various things that are measured at the patient. So the top one's showing the patient airway pressure. The second one is the volume of air, and the bottom one shows you the flow rate in liters per minute. That column of things along the right side are measured values. And the tiny numbers on the far right of those boxes are the minimum and maximum values for the alarms. So if any measured value goes outside of its alarm range, then the box containing that number would turn red and an audible alarm goes off, as well as a very bright LED that's on the front of the ventilator enclosure. So just to remind you, here's what the final product looks like, but looks are the least important part of this device. In order to get it approved, it had to be demonstrated to meet all of the requirements of the various approving agencies. This includes the US Food and Drug Administration, Health Canada, and the European Union CE mark governing body. So what does that mean to demonstrate good performance? Don't be alarmed by this giant table. This is just to show you what I mean by requirements. So there's a long list of international standards that apply to medical devices, and some are even particularly targeted to ventilators, like this one I'm showing you on the left. And so this table is an example of one such set of required performance tests that had to be demonstrated. The idea is that you just want to make sure that what the patient experiences really is what is intended by the ventilator. So we had a beautiful working machine and a lot of performance and safety tests we needed to do, But we also had a large team of scientists, doctors, respiratory therapists, eager to help us test it. And so we set up a number of testing sites around the world and shipped some of the prototype machines to those spots. So you can see we had a setup in a hospital in Monza, Italy. Elemaster is the manufacturer that helped us with the design and prototyping of all these devices. We had 2 setups at Triumph Lab in Canada. And here in Chicago, we were very fortunate to be hosted by the Cook County Hospital Simulation Lab team. They were very generous with their time and resources to help us get our test station operating in the hospital. Now, thankfully, we didn't have to do these tests using real human patients. And indeed, that would have been a completely different process. Instead, we got access to several places with sophisticated breathing simulators. And then we put the machine through a whole series of tests, some of which I showed you on the previous page, plus a bunch of others. So here's the very fancy breathing simulator. It's called an Active Servo Lung, or ASL 5000. And the way it works is you tell the device what kind of lungs you want it to act like. For example, you tell it, breathe like an active adult patient with emphysema, or pretend like you're a sedated patient with acute respiratory distress syndrome. And then it will effectively turn some knobs on the fake lungs inside the machine to make it behave with the lung characteristics that you requested. And then you can monitor things like flow and pressure and volume for each breath through the same computer that is controlling the software to communicate with the device. So actually what you're setting to get the machine to behave a certain way are specific parameters that are related to the mechanics of lungs. So let me take a brief sidebar to explain what those are. You know that we're trying to create a pressure differential in the lungs compared to the atmospheric pressure in the room. So pressure is what you generate when you direct flow into a closed system like your lung. And it also depends on how much resistance the flow sees. So pressure is really flow times resistance. The resistance can come from the breathing circuit or endotracheal tube, also from the patient's own airways, and also from the chest wall and lung itself against being pushed out. So resistance is one of the parameters that you set in the breathing simulator. Another parameter is something called compliance, and that is defined as a change in volume divided by a change in pressure. So if something has high compliance, that means it has decreased elastic recoil. And you can think of that like a pair of old socks where the elastic band is useless. So they're very easy to stretch out, but they don't spring back very well. The opposite, low compliance, means there's increased elasticity, and that's more like a hard to inflate balloon. And then the last thing that can provide pressure is something called PEEP, which is positive end expiratory pressure. And that's just the pressure that remains in your lungs after you've exhaled. So if you take all of those things together, that's what we're measuring when we measure the pressure of the patient's airway. There are several different modes of operation that commercial ventilators typically have. Some of them work by regulating the volume of oxygen that's provided to the lungs, and some will work by regulating the pressure. The MVM does only pressure regulation, which has been found to be a good mode for patients with acute respiratory distress syndrome, such as what critical COVID patients have. And that's why we decided to focus on them. So in the mode I'm showing you here, this is called pressure controlled ventilation, or PCV. That is a time cycled ventilation mode. So you set the respiratory rate and then a few other things. And the top graph is showing you how the pressure changes with time. So you, the operator, would set how many breaths per minute you want, that's the respiratory rate, and the ratio of how long you want them to inhale compared to exhale. So for example, if you set a respiratory rate of 10 breaths per minute, then each breath cycle, which is 1 inhale plus 1 exhale, would be a total of 6 seconds long. So if you then said you'd like the exhales to be twice as long as the inhales, that would be an inhale to exhale ratio of 1 to 2. And it means that you'd have a 2-second inhale and a 4-second exhale for each breath cycle. Then you also need to set the maximum inspiratory pressure, which is labeled as P-insp on that plot, and the PEEP, the positive end expiratory pressure. So on the bottom, you're looking at flow versus time. And you'll see there's an initial high flow rate, which the doctors and respiratory therapists who were working on the project told us was appropriate for COVID-19 patients because it helps them, the alveoli in the lungs, to quickly reopen. The alveoli are what take the oxygen from your lungs and transfer it into the bloodstream. So you can see in these charts that the pressure is kept constant during the inhalation. That's the flat top of the upper graph. And the flow slows down over the course of the inhalation as the lungs fill. At the end of the inhale, the applied pressure is removed by closing a valve in the ventilator, and then you see that the flow, the direction of the flow reverses, and the pressure falls back down to its baseline level, or PEEP. Now, as it happens, patients who are not capable of breathing on their own still sometimes will take spontaneous breaths. And if you didn't allow that to happen, it would be a moment of torture for the patient. And so the MVM software is written to allow patients to take a breath anytime during the exhalation. So that's what you see with that little dip, downward dip on the new waveform that appeared on the right side. So when the control software sees an acceleration of pressure change going in the negative direction during the trigger window, which is set to be during the exhalation period, then it will synchronize with the patient's desire and immediately initiate another inhale. So in PCV mode, a new breath can be initiated either after a full breathing cycle has completed, or if the patient starts to spontaneously inhale during the exhalation window. The other mode that the MVM provides is called pressure support ventilation. And in this one, the ventilator takes over part of the work of breathing. The patient maintains the control of the respiratory rate. So in this mode, pressure support is triggered when the patient initiates a breath, and that's done by that same pressure drop that we saw on the last page, the little dip at the beginning. And then the pressure is provided up to the target P-insp pressure. And the way the exhale begins is when the flow has dropped below a given fraction of the peak flow. When it drops to 30% of whatever the peak was, then the MVM valves will change state and the exhalation is allowed to begin. And then the machine goes back to waiting for another inhale trigger. If the patient takes too long to inhale again, that's called an apnea, and the system will go into alarm and force a breath, switching back to PCV. So these pressure and volume and flow waveforms give a lot of information to the doctors and respiratory therapists so that they can decide if they need to make any adjustments to the ventilator settings. We're looking at an ideal waveform right now, but let's look at how these things can vary with differences in the lung mechanics. So this is showing you how the flow and volume are affected by different levels of resistance. So in the top row of waveforms, you can see that if there's increased resistance moving from left to right, then the peak flow decreases during inhale. So the height of that peak goes down. And it also takes a longer time for the flow to get down to zero with increased resistance. So the peak goes down and it also widens out. In the second row of waveforms, what you're looking at is the patient's airway pressure, and that's the black line. So you'll remember from that equation what the airway pressure is. And in this case, it's just a square wave because it's a pressure controlled ventilation. So we're providing a fixed pressure during the inhalation, and then we remove it during the exhalation. The red dashed line is showing you the pressure of the alveoli in the lungs. And as you go to higher resistance, moving to the right, that pressure is reduced, and it also, the curve broadens out. It takes longer to get back to the minimum baseline pressure. In the bottom row, you're looking at volume versus time. So for low resistance on the left, you see you get a quick increase in the volume, and then it flattens out. As the flow slows down, the volume stops changing. At high resistance, the overall volume of air that is reduced and the change in volume happens more slowly. So that curve is broadened out again. So let's now look at how compliance affects things. As a reminder, high compliance is like an old sock or rubber band that you can stretch out easily, but it won't bounce back so well. And low compliance is the difficult balloon. So in this case, where high compliance is on the left and low is on the right. So as compliance decreases, that overall peak flow also decreases, which you can see in the top row. And the pressure of the alveoli, the red line in the second row, more quickly reaches the same value as the supplied target airway pressure, comparing the red and black lines in the second row. And then on the bottom row, you can see that the volume of air also decreases with decreased compliance. So let me flip back for a second to the resistance, compliance, and you can see there's a large variety in how those waveforms look. So now let me show you how the MVM performed. So I'm just showing you one example of the many breathing tests that were required by that international standards. And in this test, the ASL 5000 breathing simulator is set to act like a completely passive patient whose lungs and airway have a resistance of 20 in units of pressure over flow and a compliance of 20 in units of volume over pressure. And that's the text that's written in light blue at the bottom of the graph. So those are not very extreme cases, which you may recognize because of what we just looked at with the effects of changing resistance and compliance on the last two slides. The waveforms that you're seeing are what the breathing simulator measures as being provided by the MVM. So those are the airway pressure in dark red, that's that square wave, the airflow in orange or yellow, and the volume of air in the dashed pink line, which you may not be able to see that well. You can also compare what you see in these waveforms with what some of the set values were, which are the numbers in blue at the bottom. So for example, the plateau or flat top of the dark red curve is at 35 on the vertical scale, which is what the blue number for inspiration pressure at the bottom tells you was the target value that MVM was told to provide. So the breathing simulator confirms that the MVM provided the right maximum value, and it shows you, because you see several breath cycles here, it shows you there are no crazy outlier pressures occurring at any point during the breathing cycle. So it's the same idea if you look at PEEP. So the bottom of the red curve doesn't go, it gets down to, but doesn't go below the set value of 10. I won't show you the results of all of the tests, but I can assure you that the MVM met or exceeded all of the requirements that were laid out in the huge list of international standards. It performs very well. So we achieved what we set out to do. And let me finish by showing you the timeline, because that's one of the most impressive parts of this project. Moving from the concept to the first rough prototype to the final prototype was really fast. It was much faster than anything we normally do in particle physics. It took only 1 month to go from the concept to a machine that demonstrated its functionality, and only 42 days to go from that concept to approval by the US Food and Drug Administration under the emergency use authorization, which means it was approved specifically for use during the COVID-19 pandemic. After our approval in the US was obtained, we then moved to get approval in Canada as well. And the Canadian approval required a full certification of the software, which took a bit longer. But this approval was just granted 2 weeks ago on September 30th. And the really great news is that the Health Canada approval came with a contract from the Canadian government to build 10,000 units. So some of them will be kept in Canada, but many of them will be sent to other places in the world that are in greater need. Currently, we are awaiting approval for use in the European Union, but we're hoping to achieve that milestone very soon as well. And as a closing thought, I wanted to share with you this wonderful quote from Philip Livedall, whom you'll remember was one of the key players in the design and commissioning of the accelerator for proton therapy. He's summarized really beautifully how I feel about this whole process, so I won't even try to top him. So thank you all for listening, and I'd be happy to answer questions.
So thank you, Jen. That was wonderful. And I want to tell everyone that we will have this recorded video available soon on events.fnal.gov. And now we do have quite a list of questions, so I'll just start. Does your ventilator have any feedback mechanism with the patient's measured blood oxygen level in order to increase blood oxygen, say respiratory rate or more oxygen in the mixture?
No, it doesn't. So we rely on the nurses and doctors to have an external blood oxygen sensor, and then they would have to adjust the machine by hand. Mm-hmm. That was partly because we wanted to keep it as simple as possible, and that's adding complication adds cost as well.
Mm-hmm. How do you handle it if the patient starts to cough?
Very good question. So I didn't have time to get into all of the details about that. There are various triggers that the machine will sense if the patient is fighting against it or doing something that causes a large change in pressure, like coughing. And it will try to resynchronize with the patient's breath after that. So hopefully not providing them more discomfort than they're already in.
Mm-hmm. So what others in the world are creating competitors to this idea? And how different are the different competitors?
I know there are quite a large number of teams trying to design and make available simple, cost-effective ventilators. I know about a few of them, but it would be better if people go look up for themselves. I don't like to think of it as competition. I think we're all in this together. It's, the more available ventilators there are, the better for everyone. So it's not a competition. It's just different teams started working on it in different areas and went in slightly different directions. And the more working things we have at the end, the better for everyone.
Yeah, I guess we had a similar question, which I can't find now, but just since it's related, I'll paraphrase it. That was that in the beginning, we heard a lot in the news about shortages of ventilators and things like that. But it seems like that has gone away. And do you know why? And is it just that companies started making them or why?
So it's true, we did expect there to be a much larger shortage of ventilators than there seems to have ended up. Part of it is probably that we did manage to flatten the curve a little bit. So the number of patients in the ICU at any given time was probably a little bit lower than the initial projections. I know that also manufacturers started making more as fast as they could. But I think there was probably also more in backup that hadn't been counted, but I don't know for sure.
Mm-hmm. And this device sounds to be like a CPAP. So does it have any relation to that?
I'm not a medical doctor. I think there are some similarities, but I don't think it's exactly CPAP. And I can't say in any more detail.
Mm-hmm. Mm-hmm. Okay. So could you say again how many of these devices have been built and are in use right now?
So we just received the approval in Canada 2 weeks ago, and there was a contract to build 10,000 of them. So actually the manufacturing began before we got approval because we were quite certain that the approval would come through. So I think those machines are starting to be available right now. I don't know if any of them are in use yet.
Okay. Um, so someone says this has been a great talk, and why is positive ventilation preferred to negative? If the negative ventilators are non-invasive, then that somehow sounds better.
Yeah, you're right. It does sound better. You saw that they're pretty cumbersome. So those iron lungs, they had huge wards full of big pressure vessels with humans sticking out of them. That's one reason. There are smaller devices that like make a encase around your chest, and I know that negative pressure ventilation is still used sometimes, but you'd have to ask a medical doctor why one is preferred over the other.
Mhm. So is the Arduino or the Raspberry Pi useful in other Fermilab projects?
Yeah, they're fun little devices. I know a couple of my friends who are using them to monitor various things in the accelerator. Lots of people use them for home projects.
So we have a question from the beginning of your talk. What happened to the neutrino therapy lab at Fermilab?
So it was shut down in 2013, I believe, because I believe part of the accelerator couldn't accommodate anymore. We needed to use that to do other things. And there was some also funding is always a problem.
Mhm. So another question we had from that section of the talk, proton therapy, all these particle therapies can be quite expensive, as you said. And are there any statistics, do you know of any statistics that shows that this really saves lives in large numbers, given the expense?
So every cancer is its own individual snowflake.
Right.
And so it's hard to make a pile of this kind of cancer and that kind of cancer. There are clinical studies that show, for certain kinds of cancers or certain locations of cancers, the particular types of therapy are very effective. But it's not, you couldn't say, I have any type of cancer and proton therapy is the way to do it. So it's really dependent on which kind of cancer. There are lots and lots of clinical studies that show that it can be effective for certain types of cancers. I can't point you off the top of my head to one, but if you go search, there are quite a number of good resources on the web to find out why people think proton therapy or neutron therapy or hadron therapy is useful.
Mhm. And I think I have one more question about the MVM. Is there any research still going on to modify the current device and make it function even better? Or is that possible?
So the volunteers who helped design it, we're no longer involved with modifying the device. The manufacturers, who are one in Italy called Elemaster, and in the US and Canada, the manufacturer is called Vexos. So Elemaster and Vexos have partnered to build these devices. And there are probably going to be more advanced versions of it in the future. after we get full approval. So right now we have approval for emergency use during this pandemic, and there won't be, so we won't modify it for the version that's used during the pandemic. But after that point, then the manufacturers could add some of there are a number of bells and whistles that could be added in that we didn't do because we were trying to get it out the door quickly.
Okay. I'm looking for any more that I didn't cover yet. Did you discover any inconsistencies in performance criteria from the various international regulatory bodies, like when you're combing through all that documentation that I know you did?
Yes. So it is very interesting. So the different regulatory bodies, I wouldn't say that it's in conflict, but they often want to see slightly different things. So the full panel of tests that we did, we tried to encompass all of the above, which meant that sometimes we would do a test for body A that was very slightly different, that we would have liked to do only one test, but we had to do a second one with one thing slightly changed so that we could do the whole slate of tests and then write up the documentation and try to make everyone happy. But I don't think there were any directly conflicting things. They are international standards, so supposedly everyone is supposed to be adhering to the same set of standards.
Okay. Well, thank you very much, Jen. I see lots of compliments in the QA boxes over here. And I want to remind everybody again that this video recording will be available offline. Tell your friends. Thank you.
Thanks.